Hello, my name is Brayden Kent. I am a graduate student from Ontario Tech University, and today I'm presenting tissue discrimination from impedance spectroscopy as a multi-objective optimization problem with weighted naive Bayes classification. So I'll begin with some background. Essentially, we know that there are some challenges in targeting lesions under ultrasound imaging. When we do procedures like biopsy and brachytherapy, we are inserting a needle into the tissue to try and target a lesion, whether that be to take a sample in biopsy or treat it with radiation and brachytherapy. However, in some tissues, such as the prostate, we know that there are tumors that can't be identified under ultrasound. So how can we improve the targeting? Well, we know that tissues have different dielectric properties, so much so that we can tell the difference between a malignant tumor and the healthy tissue surrounding it. Shown on the bottom here are two examples of probes that are designed to do just that. We have the inject biopsy needle, where they have this central core electrode, and the needle shaft is acting as another electrode, which forms what we call a bipolar spectroscopy arrangement, where we can measure the electric impedance at the tip of the needle and determine what type of tissue it's in. NASA and Bioilluminate have done a similar design, where they have a central core electrode and the needle shaft is the other, as well as some additional sensors. So how can we go from electron impedance measurements and classify tissue? In this paper, we explored the use of the RPD-NSGA-II algorithm to fit the electron impedance to a model. From there, we can decompose the problem into fitting the electron impedance, phase, and magnitude to determine these model parameters. And from those model parameters, we can classify the tissue using a weighted naive Bayes classifier. This presentation is going to talk about our electrode embedded needle prototype, the algorithms to fit the electric impedance to the model, our classification method, and some future work. For our electrode embedded needle prototype, we took a standard 18 gauge brachytherapy needle and we fed a PTFE coated copper wire coaxially down the shaft. So again, the copper wire is acting as one electrode, the needle shaft is acting as the other. That's what we call a bipolar arrangement. When we feed a sinusoidal voltage across those electrodes through the tissue at the tip, if we measure the current via Ohm's law, we can figure out what the electric impedance is. We connected our probe to the quadra, an impedance analyzer, configured to measure the impedance at 23 different frequencies, and to take the average of 10 measurements. For our experiments, we wanted to just validate the system, so we created gelatin phantoms, where we were able to change the conductivity by altering the amount of salt that we put into the gels. Shown on the bottom here are the electron impedance spectra for the three different types of tissue. We have 4 samples for tissue 1, 4 samples for tissue 2, and 4 samples for tissue 3. And you can see that there are some unique features amongst the electron impedance. Note, however, that there is some high deviation at the lower frequencies, and at higher frequencies, there is a bit more of a convergence. And you can see that there is some variability, some noise in the measurements. So there's a motivation to fit these measurements to an equivalent circuit model, such that we get these fit lines that run through the measurement points to smooth out some of that noise. So in order to fit the data with this level active model, and we decided to go with the double dispersion cold model, as it had a relatively good fit to our data. These elements here are known as constant phase elements, and they act as pseudo-capacitors, where they have a impedance of 1 over j omega c, where s, the Laplace variable, is j omega, and we raise it to the exponent alpha, which we call the dispersion coefficient. Shown on the right here is the impact of changing that value for alpha and how it affects the impedance over the frequency. So granted we know what model we're going to use, how can we find values for each of these parameters such that the model impedance matches the measured impedance? We decided to go with this method here, known as reference point based, dominance-based, non-dominated sorting genetic algorithm 2, which is a multi-objective approach based on a genetic algorithm. We create 100 population members. Each population member has a potential solution. We initially define our population randomly between bounds, and through the optimization process, we are trying to find the Pareto front where we are satisfying our two objectives, minimizing the impedance magnitude error and minimizing the impedance phase error between our model and measured values. We have set up our optimizers such that we want all of our 100 solutions to be in the Pareto front. And we achieve this by going through a typical genetic algorithm fashion where we have our initial population, and we perform our genetic operators, mutation, and crossover. We evaluate the fitness of each of those population members, and the candidates that have the best fitness are more likely to survive and produce a child population. We iterate that procedure until our stopping criteria are met, and at that point, all of our solutions are in the Pareto front. We utilize the reference point dominance condition to help get a better representation of the Pareto front. Shown here are some of our conditions. And just to illustrate here, each of these black lines is one of these population members, a solution to fitting the impedance. After 100 generations, there is not a very good fit, but after about 2,000 generations or so for this problem, you can see all of the solutions are starting to converge and are a good representation of the measured impedance. Shown here are, again, 4 samples for each tissue type and the values for the 7 parameters. And as we can see here for our infinite, if you want to tell the difference between tissue 1 and say tissue 2 or tissue 3, you'd probably look at our infinite because it is distinctly different than the other 2 tissue types. But you might not want to use, say, C2 because the values are within the same band. Looking closer at tissue classification, we went with a weighted naive Bayes approach, but let's break it down into its pieces. We started off by defining our database. Essentially, for each tissue type, we had a number of samples, and each sample had 100 population members. For our test samples, we had 1 sample going in, and we create 30 population members and find the Pareto front. We then classify each population member using our naive Bayes classifier, and then we look at the labels for each population member. So for example, say population members 1 through 29 were identified as tissue 2, and the last one, number 30, was identified as tissue 3. Because the majority of the samples were identified as tissue 2, the overall label for the test sample would be identified as tissue 2. So looking closer at our weighted naive Bayes classifier, it operates on the idea of looking at probabilities, a probability of a parameter value for a certain class. We multiply out the probabilities, and we look at overall which one had the highest. And we take that tissue label and we assign it to the test sample. We modify the probabilities using these weights that we found through a random walk method, essentially performing this classification procedure, but only using the database, not using the test samples. Overall, you can see our results at the bottom here, where for tissue 1 and tissue 2, we achieved perfect classification. Tissue 3 struggled somewhat, sometimes misidentifying some of its samples as tissue 2. So in conclusion, this paper has presented tissue classification from an electrode-embedded surgical needle using the RPD-NSGA-II algorithm with a weighted naive Bayes classifier. So there is some future work that needs to be done. The core of the developed prototype is currently blocked, which prevents it from performing its surgical functions. So either taking a sample in biopsy or depositing a radiation seed in brachytherapy. However, we have seen other electrode designs in the literature where they have solved this issue by manufacturing the electrodes on the surface of the needle, leaving the core free. We have done in another paper measurements with ex vivo tissue. However, we have still yet to see if this procedure is accurate enough to discriminate between healthy tissue and malignant tumors. And lastly, we need to develop these systems for real-time classification. Currently, the method is computationally expensive, and we need to find some efficiencies such that we can, in real time, classify tissues for surgical applications. I'd like to thank you for attending my presentation, and I would hope you enjoy the rest of the conference. Thank you.